Hey there! Welcome to the final stage of our video series on 1D and 2D kinematics for AP Physics C Mechanics. In this final video, we're going to be covering really the culmination of everything we've been doing up to this point in this unit, which is projectile motion. Probably the cool, applicable part of this unit that you all were waiting for. So, without further ado, let's jump into it. And I'm really just going to cover the basics and the basic concepts that you need to know for projectile motion, and then we'll do a lot of examples with these concepts. So projectile motion is defined as a very specific set of conditions that need to be true. So a particle is in projectile motion, firstly, when that particle is in free fall, meaning the only force acting on it throughout the entirety of its motion is just gravity. So it can't be a rocket firing its thruster until that thruster has burnt out. It cannot be a person on a bungee cord where that bungee cord has any amount of tension that is pulling up on the person. That is not projectile motion. It has to just be flying freely through the air with nothing but gravity. And I guess tied to that is that there then is only an acceleration in the negative y direction. So it is not projectile motion if it is experiencing an upward acceleration relative to the ground. Keep in mind that we will do things later on, especially in the electricity and magnetism unit, where something will experience parabolic motion like you see up here, and you can use all of the projectile motion equations for it, but it is technically not projectile motion because it's not in the negative y direction. And finally, really the important one to remind yourself of, because it saves you a lot of time, is that the motion in the x direction is constant velocity, meaning that whatever this thing launches with, v naught in the x direction, it is going to stay that velocity for the entirety of the flight in our perfect little physics world. In the real world, that doesn't happen because of air resistance, but let's not go there. All right, another important concept is that an object in projectile motion follows a parabolic path, if you didn't notice that up here. This is very prevalent and it's very fun to observe once you know in real life. You see this all the time with really cool fountains that shoot little jets of water in parabolic arcs. If you just simply throw a ball, or you maybe watched all the basketballs or all the three-pointers being thrown during the Olympics this summer, or if you want to watch a lot of free throws in basketball, you see parabolic motion from projectiles all the time. It's very predictable, very cool, and mathematically pretty nice. This can be modeled with a quadratic function, as people discovered very long ago, like we briefly covered in the derivatives video. And finally, an object's vertical velocity is always 0 at its maximum height h, and that's explicitly given right here. This is important to keep in mind because this gives you an extra piece of information to use if you're trying to solve for something at the maximum height. Like, let's say how long it takes to reach that max height. You may want to do that if your goal is to, say, figure out like at what time something needs to deploy parachutes at the top of its trajectory, or maybe for like a firework, a timed firework that needs to know how long before it has to explode. Anything like that, you never know. Now, for certain systems, especially this one that's pictured here, that's a ground-to-ground projectile, there are some helpful symmetry tools that you can also take advantage of. So firstly, also at the maximum height h, generally we can say that it is going to reach that height at half its total time t. So whichever thing you find first, the time it takes to reach its maximum height, or the time it takes to go the full distance all the way to the other end, half of that height, or half of that time, is going to be the time it takes to reach half that total time is going to be the time it takes to go through half of its trajectory, always. And another helpful thing to keep in mind if you have to figure out something about the final velocity is that a projectile's launch velocity is equal in magnitude to its final velocity, but as we're going to find with one of our examples coming up, the final y velocity is going to be the negative variant of the initial y velocity. So important to keep in mind, and we'll see that firsthand in a second. All right, so really the equations for projectile motion are no different from the kinematic equations we've already been using and are very used to. However, it is worth applying some of our concepts to kind of distinguish between what's going on in the horizontal direction versus the vertical direction, because we do have two-dimensional motion going on here. So on the position front, we have our nice little constant motion, or our nice little zero acceleration equation. That's x equals x naught plus v naught x times t. This is exactly how it appears on the AP Physics C formula sheet. Now, this formula could also be rewritten as delta x equals v naught x times t. That's generally how most of you will probably prefer to write it. But in case you have some kind of initial position that isn't the origin, this equation is also important to keep in mind. Now, if we want to take the velocity of that, we quickly figure out exactly how and why our velocity is constant, because we eliminate this x naught entirely, and we're taking the derivative of position. And so through doing that, we eliminate this t, and all that's left is initial x velocity. If we take the derivative of that again, well, now we are differentiating a constant value. So the acceleration in the x direction should be 0. Now, in the vertical direction, this is where things are exciting and fun. So again, I'm going to stick to this y and y naught format. And in this case, because we are accelerating in this direction, we now have to use the full quadratic kinematic equation. And in this case, I have done a substitution for a with g. There is an important thing to keep in mind here, which is that technically this term, the squared term, should be negative. The reason I did not do that is something we're going to find later with some of the equations that we'll be deriving. And that's that generally I find it easier to plug in the negative quantity later on rather than generalize it here. So if we take the derivative of that with respect to time, then we get the y velocity as a function of time. And in doing that, we eliminate this y naught here. We eliminate the t in this middle term, and we take down the 2 and subtract this 2 by 1. And as a result, we get v naught y plus gt. Again, we derived this equation originally in the derivatives video after that Galileo data thing. And finally, if we take the derivative one more time, we get acceleration in the y direction. And surprise, surprise, this gives us a singular constant value, a singular constant acceleration that is true for the entire problem. And that is the acceleration due to gravity g in the negative y direction, or straight downwards. All right. So with these equations in hand, we're going to run through a bunch of fairly lucrative projectile motion problems so you can get back into the groove of things, and you'll be back up and running in no time. So let's jump right into it. All right. With this problem, we've got 3 things that we're going to be solving for, all 3 of which are completely symbolic, meaning there are no numbers in this problem besides y equals 0. We're going to be making some additions to our toolbox with this because we're deriving 3 handy equations for solving for the total time of flight, the maximum height of a projectile, and the total range of a projectile, meaning how far horizontally this thing travels along the x-axis. So with projectile motion, we're going to keep a couple rules in mind. First off, again, we're going to assume that this thing is in free fall, meaning the only force acting on it is gravity. That is going to give us some slightly altered kinematic formulas over here, where we've got, instead of acceleration, we've got acceleration due to gravity g. I have kept the plus sign here, and that's just because we're going to be specifying that g is a negative quantity when we write it out later. This is important because we're going to have both positive and negative velocities at some point in this problem. I've also gone ahead and given the derivative forms of the other kinematic formulas that you can get from the position equations. These could be useful later, but it's just nice to have them here. All right, and then finally, there really is only an acceleration in the negative y direction. Again, we're going to be specifying that later, and the motion in the x direction is constant velocity, and that's going to help us get the range once we get there. With all of that out of the way, I will go ahead and just read it off. We have an initial angle, theta. We have an initial velocity, v naught, and it passes over level ground. So it's a ground-to-ground problem. This is its own piece of information, except you kind of have to extract something from that. And again, we have a maximum height, capital H, a distance r, and a total time of flight t. We're being asked to derive expressions for all three of those in terms of the given information here and any known fundamental constants like g. All right, so let's start with t. And before we do that, there is one thing that generally is always helpful to solve for, and we're going to find it as we start writing out our information here. The first thing is, well, we can use an angle, so we'll go ahead and write that. We have an initial velocity. And the last thing, if we're finding the total time of flight, notice that this projectile starts here vertically in the y direction, and it travels all the way through this arc and then lands technically at the exact same vertical spot as it did over here, meaning this projectile traveled no net displacement vertically. That means that if for a ground-to-ground problem, from beginning to end, the delta y is always 0, or the change in y is always 0. That's going to be helpful for us because in these equations up here, well, these are in AP form, which they always include the initial position separate from the final position, but delta y is really just a combination of those two. This would be saying y minus y naught is equal to 0, in other words. So just subtracting this thing over to the other side. Now, the other thing that's kind of missing from this equation before we can actually start doing some math is that we need the initial y component of the object's velocity only. And so I'm going to suggest that we find the components before anything else. And I'm going to do that up here. And for components, remember that we're really just envisioning a right triangle with whatever the initial velocity is right here. So we've got the x component going along here, and added to that vector is the y component going up here. So it's going to be v naught x and v naught y and v naught y. And if we're looking at this angle right here with the horizontal, then this is going to be the opposite side. This will be the adjacent side. So v naught y is generally associated with sine, v naught x generally associated with cosine. So over here, really the quick way to go about that is to just multiply the original vector by its associated trig function. So v naught cosine theta will be v naught x, and v naught y will be v naught sine theta. And once we have those components, those are helpful pieces of information that we can use down here. So I'll go ahead and write that here. And now we are pretty much good to go. The last thing we need really is that we do have an acceleration due to gravity, g, that we can take advantage of. All right, so now let's take all the information and solve. It's looking like the best equation to use here really is this one, because it has g, it has v naught y, it has delta y. So let's go ahead and use it. So I'm going to go ahead and write this in the form delta y equals v naught y times t plus 1/2 g times big T squared. And I'm going to specify this as negative g, which would be like negative 10 meters per second squared, in other words. All right, and now we can substitute. Delta y is 0. We've got v naught y, which is really v naught sine theta times big T, and minus 1/2 g big T squared. Okay, now we can go ahead and subtract one of these terms over to the other side. I choose to subtract this term over to the other side. So we're going to make that 1/2 g times big T squared equaling v naught sine theta t, or times big T. Okay, and this is quite a momentous occasion. This is our first splinky of the year. A splinky really just means anytime you have a common term on all parts of an equation. That generally means that you can safely divide all sides of that equation by that variable and eliminate it from the equation with no repercussions. In this case, you're not fully eliminating it. You're eliminating it on the right side of the equation. But over here, if you divide this term by t, you are getting rid of the squared in the t term. You're left with one remaining t. And so as a result, we get 1/2 g big T equals v naught times sine theta. And after this, it's fairly easy to solve for t on its own. You multiply both sides by 2 to get rid of the 1/2 on this side and divide by g. So t equals 2 v naught sine theta divided by g. And that is a one and done formula for big T. Now, we can go ahead and add this to our toolbox. This is a very helpful skill overall to be able to take advantage of. This formula means that if you have a programmable calculator, like most of you do, or if you're just writing a Python script or something to solve for the max or the total time of flight of any ground-to-ground projectile, you can plug in, you can write this out, this formula, and then just set the parameters, the numbers you plug in to be v naught and theta and g. And if you do that, you will be able to just hit a button and solve for t right off the bat. It's very helpful. All right. So the next one over here is the max height h. So we'll go ahead and write that as a big question mark. And again, we're going to use a lot of the same initial information here. I'm still going to be taking advantage of the theta, the v naught y. We cannot take advantage of delta y equals 0 here. Why? Well, we're not exactly going the full distance now, are we? We're going over to here where our delta y is certainly not 0. We start at the ground and we gain a height h, which is what we're solving for. So we cannot use that information here. What we can use, however, is we can pull something out of our toolbox, and that is that v naught, or sorry, we'll call it vh is equal to 0, meaning a projectile's vertical velocity, we'll make that vhy, is equal to 0 at its maximum height. This object temporarily reaches a stopping point vertically. Okay, so we will take advantage of that, and that'll be its final velocity, so to speak. And we still have g. So we'll have theta, we'll have v naught, we'll have negative g, and we have vhy equals 0. Okay, so in this case, we're going to let's see, with the variables that we have, technically none of the equations that we have immediately available up here are there, but on the AP formula sheet, if you take a close look, there is an equation that matches this set of information quite nicely. So we're going to use vhy squared equals, and we're going to again need to use only vertical velocities here. So again, we're going to use v naught y squared plus 2 times negative g times big H. And in this case, we have a little bit more substitution we need to do. We're going to say 0 equals, this is going to become v squared, or v naught squared times sine theta squared plus, or sorry, minus 2 times g times big H. Now, again, we're going to subtract 2gh over to the other side, and we'll get 2 times g times h equals v naught squared times sine theta squared. And then finally, to solve for h, we just need to divide by 2g. So h officially will become v naught squared times sine theta squared divided by 2g. And that is our final result. Again, another thing to add to our toolbox there. That's pretty handy. All right. And finally, we're going to solve for range. This is honestly the most famous of these three quick equations. This is something known as the range equation. You can look it up, you can get a spoiler if you want, or you can try to solve for it before I do, whatever you like. But this one is pretty helpful because this is generally what you want when you're launching a projectile. You want to know where it's going to land so you can do a cool trick shot and impress your friends. In this case, we're going to again be using all of the same information. However, because we're working with horizontal range here, we are actually going to ultimately need to plug everything into this equation right here. And one thing to note with this equation is that this t here really needs to be big T. It's coming back. And again, this x naught here can get subtracted over to become delta x, and that becomes our displacement, so to speak. So I'm going to write that out here. Delta x equals v naught x times big T. And this is something that you can honestly say that you already solved for over here. You've already done the work for this, so let's not do that work again. And we have v naught x over here. So really, this is a simple matter of plugging everything in. Surprise, surprise, we've already done all the work. So over here, we're going to plug in v naught times cosine of theta this time. And big T, we're very familiar with. That's 2 times v naught times sine theta divided by g. And as a result, we will get 2 v naught squared sine theta cosine theta all divided by g. You might be thinking, that's a bit of an ugly equation. You are right. However, there is a trig alert among us here. There is a nice trig identity, which states that 2 times sine theta cosine theta is equivalent to sine of 2 theta. You can look up the proof if you're interested. This means that we have a 2 here, we have a sine theta and a cosine theta all multiplied together if we just rearrange a little bit. So we can turn this equation, this range, capital R, into v naught squared times sine of 2 theta all divided by g. And that is our very nice, very famous, in fact, magical range equation. And again, as long as you have a ground-to-ground projectile or something that's roughly that, you can use this equation, just plug everything in, an instantaneous solve for the range. It's very handy, so let's add it to our toolbox. Call it a day. Nice. All right, and this next problem is a bit of a doozy. Now, I'd like to preface this by saying that this problem has a lot of different ways that you could go about solving it, and I'm not going to stop you from wanting to solve this problem in any specific way. I'm simply going to go show you the way that I kind of like the best as a road trip person. What I mean by that is I'm more of a journey rather than destination sort of person. And while you can use the quadratic formula to solve this problem outright, I would prefer to solve it kind of in pieces so that you get more information about the object's motion as it travels between each of these points. So I'm going to be doing it that way, but if you would like to pause this video and solve it the way that you think is best, I want to encourage you to do so. Without further ado, we have an object, a cannonball in fact, being launched off of a 405 meter cliff. And it's launched with an initial speed of 150 meters per second at an angle of 53 degrees to the horizontal. Okay, I'm gonna go ahead and write underline all of that. Sorry, it's behind there. And we just have 3 points that the ball passes through in its trajectory. These are helpful key points that are gonna help us create these graphs over here to the right later. And so the problem is simply asking how far from the base of the cliff does the ball strike the ground? So we're trying to find the range over here. Now you might be thinking we just solved for a range equation in a previous part. We cannot use that necessarily from beginning to end here. And that is because this is not a ground-to-ground projectile. Remember that the range equation and all of those equations, as a matter of fact, really only work for a ground-to-ground projectile. We can still use it at some point in this problem, however. And then we're expected to find graphs of the ball's velocity. All right. So first off, we'll go ahead and just write our actual objective here. We need to keep this in mind as we go through. And I'm going to write out the information that we have from the get-go. We have a total delta y of 405 meters. We have an initial velocity of 150 meters per second, and we have an angle of 53 degrees. Now, right off the bat, I would recommend, again, solving for the components of velocity right now, because odds are you are going to need them later, so it's helpful to just have them written out already. So again, v naught x is going to be v naught times cosine of theta, and v naught y will be v naught sine theta. Cool. Those are helpful. And we can solve for those here. So we'll go ahead and do that. This is going to be 150 times 53 degrees. And that'll amount to about 90 meters per second, all in all. Okay. And then same thing over here, 150. Oh, whoops. There should be a cosine there. My bad. Oh, whoops. And over here, it'll be sine 53, which amounts to about 120 meters per second. Okay. Now, we need to think about a game plan here because this is a multi-step problem. If you would like, you can solve this problem again in one step using the quadratic formula. I'm going to avoid doing that because I personally don't really like writing that equation out. But again, physics is physics, and there's no real wrong way of doing it if you get the right answer. So if I wanted to solve this in steps, mostly to help me fill out the different parts of the graph, I want to try and aim for different velocities. And as it turns out, solving it using that can be fairly helpful if you notice from a previous example we did, because the velocity is changing by a constant amount each time. It's a fairly linear process, so generally the equations themselves are going to be pretty nice to work with. So I'm going to think maybe I want to solve for the velocities at A, B, and C first. Before anything else. So I'm going to make that step 1. I'm going to solve for VAY, VBY, and VCY. And one helpful thing with that is that it's going to give me one of the 3 crucial pieces of information at all 3 of these points, which is going to help me be able to solve for certain information better, especially knowing that we have another one of the pieces of information by default, which is gravity. Okay? Next, let's say, well, we're going to need times as well, because we need to know the time that elapses between different points on this graph. So I'm going to say we probably need to solve for those too. We can fairly easily find the time that it takes for a projectile to go from launch to B, because we derived a formula for that. And notice that as far as launch to B is concerned, that basically is a ground-to-ground projectile. It's just that it travels through the ground, so to speak, after that. So let's say we want to find the time that it takes for the projectile to reach position B next. And then maybe step 3 is we need to figure out how much time elapses between B and C. So we'll find and label that as TBC, let's say. And then step 4, I think after that, well, we have gravity, we have the velocity between these 2 points, we have the time that elapses between those 2 points. Odds are we will have enough information to solve for the range at that point using all of that information together. So we'll say at that point, hopefully we can find the total range R. Okay, so let's put all of this into practice. For step 1, let's see if we have any like really trivial velocities here. So first off, we have velocity A, which we know is going to be, well, at least velocity Y is concerned, it's going to be 0 there due to a nice little concept in our toolbox. And VB is also going to be fairly nice because VBY, we can also pull another tool out of our toolbox because we're assuming it's a ground-to-ground trajectory that says that it's going to be negative V0 Y. And that is also from our toolbox. So it'll be negative 120 meters per second downwards in this case. All right. So really it's VCY that I think we're going to have to actually do some work for. So VCY, there's a question mark here. For this, well, we already know VBY, so let's go ahead and assume we have that information. And then we know that G is likely to be negative 10 meters per second squared. At least I'm going to assume it's 10 here, not 9.8. And then let's see, what else do we have? Well, we do have the delta Y. We're going to know the displacement from here to here is 405. So that is our third piece of information. We have delta Y equals, notice that it's down between these 2 points, so it'll be negative 405 meters to the bottom. So we have that, we have that, and we have that. We've got 3 pieces, so we are good to go. Let's solve. So we've got 2 velocities, a G and a delta Y. Taking a look at our AP formula sheet, that rings that we're going to be solving for ZVY squared equals V0 Y, or sorry, VBY squared plus 2 times G times delta Y. Now we'll substitute, we're solving for VCY outright, so really we'll just square root everything and get it by itself from the get-go. And that leaves us with square root of, we're just going to call that 120 squared because the negative sign doesn't matter ultimately there. And then we've got 2 negatives multiplied together, so that'll cancel out and leave this positive, so it'll be plus 2 times 10 times 405. All right. And once we solve for that, we should find that, well, again, because we're square rooting something that we don't know is positive or negative, we conceptually know that this is going to be a negative velocity. So, and once you solve for this, you're going to find that it is negative 150 meters per second. And again, that is the velocity that this projectile is traveling downwards over here. All right, so that's step 1 done. Cool. So next, step 2, we need to find the time of flight from launch all the way to B over here. And for that, I'm going to pull a handy-dandy equation out of our toolbox. It's big T from a previous example. So we're just going to say big T over to B is 2 times V naught times sine of theta divided by G. And for this, it's kind of nice. We just need to plug and chug. So we'll go ahead and do that. We've got our V naught is 150 meters per second. It's sine of 53 degrees. And we're dividing that by negative 10. Technically, this should be negative 150 as well to cancel out the negative sign. Once we do that, we will find that the projectile takes 24 seconds to travel from here to here. So 24 seconds is our TB. Cool beans. All right, that's step 2 done. Cool. So next is step 3. Now for step 3, we need to find the time elapsed from B to C. So T, B, C is a big question mark here. Now we don't really have any nice tricks up our sleeve for this one. We are just going to have to solve outright. So we'll assume we have all the information we need at this point. In fact, I'm going to use the same set of information that we used in part 1 over here, all of these initial velocities. So for that, the best equation is going to be one that we haven't actually used yet with this new table, and that's this one right here. This Vy right here is the velocity at point C. This V naught Y is the velocity at point B, and then G and T are the remaining 2, and those should be trivial. So we're going to use VCY equals V naught Y, or sorry, VBY plus G times TBC. Lots of E sounds in this video. Okay. And then we can go ahead and substitute. So VCY was a negative 150 meters per second. Oh, I don't need to write units there. And then it'll be negative 120 meters per second for VBY. And then we're going to go ahead and just plug in the minus there. So it'll be minus 10 for G times TBC. Okay. Now there's a negative sign on all terms, so we could just get rid of those if we wanted to. I'll go ahead and do that. Now you'll find that it works itself out later if you don't like that. And so it's going to be 30 equals 10 BC, or 30 equals 10 TBC. So we divide both sides by 10, and we will find that TBC is approximately 3 seconds. So it takes 3 seconds for this projectile to travel from B to C, or to travel that 405 meter distance. Cool. All right, and last but not least, step 4. This is the big apple. This is where we find the range. So for the range, at this point, we have pretty much everything we need. We have V naught X, and remember that the range of a projectile only depends on V naught X and the time overall. So we have the total time that's elapsed. We know how long the projectile takes to travel from here to here, and then from here to here. So we're good there. And we have V naught X. So we are good to go to solve for the range. So we need to find the total time. We'll just call that big T. And that's 24 seconds plus 3 seconds for the 2 segments of the trip. And that'll be 27 seconds total. And then we have V naught X, and that is 90 meters per second. So range is going to equal V naught X times big T. And that'll be 90 times 3. So the range of this projectile from start to finish will be, 27 seconds. And so the range of this projectile from start to finish will be 2,430 meters. That's a long way. That's almost 2.5 kilometers. All right. And that is the total range of this projectile from start to finish. And I'd like to reiterate that you could have solved for this number from the very start using the quadratic formula. So if you're in a pinch and you just need that number and you don't really care about all the graphing stuff that we have to do now, that's a pretty good option, especially if you have a program for it in your calculator. All right, so now let's find our graphs. And the graphs are going to be pretty nice. They're all velocity graphs. And because this object is constantly accelerating, that means that we are almost always going to have, as evidenced by this row right here, either a linear graph in the y direction or just a straight up constant graph in the x direction. That means our constant graph is going to be quite nice. Let's do that one. Ooh. All right, so we have v naught x here, and it starts moving at that speed from the get-go. So at 90, that's going to be right here, and it's going to travel that distance for a grand total of 27 seconds before it hits the ground. So that's going to be 6:27 right here, give or take. Whoop. Yeah, right there, give or take. And then this object travels down to the ground, or stops, we'll assume, and then it's just traveling with 0 velocity all the way to the end. All right. And then for Vy, let's set a couple of key markers so that our graph looks a little bit nicer. So well, our first thing to know is that, well, the object starts traveling vertically with a velocity of positive 120. So that's going to be 110, 120 right here. The next marker that we have is when it's well, we know its final velocity is negative 150 at 27 seconds. So that'll be right here, here, all the way down here, right there. Okay. And finally, we do know that the projectile at point B right here is traveling downwards with negative 120 meters per second. So at point B, that happens 24 seconds in. So that's going to be right here. 24, and we need to find 120 right here. It looks like it lines up pretty nicely. So at that point, I think that's enough information to go off of. You can pull another thing out of your toolbox and say that the object turns around, or it's at its maximum height at 12 seconds, TB over 2, because we can apply the ground-to-ground logic there as well. So if we did everything right here, we should find that the line that we draw through all of these points lines up at about 12. So let's see. We'll know it's right if we did that, which is quite satisfying. Oh, and it's snapping, which is a little annoying, but that's okay. We can have a little bit of error in our graph. So I'll just put it there and call it a day. Oh, how do I get rid of this? Ah! Oh gosh, what is going on? Whoa. Okay, well, go ahead and delete that. Oh, and it deleted our graph. All right, so let's draw a line and see how well we did. We've got that all the way over to that, and we'll go ahead and call it there. And that line looks okay, and it looks like it about lines up with 12, considering the line is not perfectly lined up there. So I would say we did a pretty decent job with that. And that is our graph. So again, I hope you did this problem the way that you see best, or you at least explore some of the other options available. You could have very well solved this in 2 parts by finding the maximum height and then solved the free fall equation from there. Or you, of course, could have used the quadratic formula. Whatever the case, this is a pretty good comprehensive problem, and that is all. Cool beans.